record, and we're recording. Excellent. Okay. So if you guys remember from the last couple of days in class, we've been talking about neuromuscular anatomy. So we've talked about skeletal muscles, individual kind of structures. We've talked about some of the key structures in the nervous system and how those things are going to help us play a role of connecting the brain down out to your skeletal muscles. Okay. And then we started kind of at the end on Monday, putting some of that all together. So if you need to move, if you need to generate force, how are we going to basically have the brain decide, let's do this, send these signals all the way down, kind of out to the individual actin and myosin molecules so that we can form a cross bridge. And then when we need to adjust the force level that we're going to get, how does the nervous system kind of play a role by altering motor unit recruitment and things to be able to help us modulate this? Because we're really, really good at controlling how much force we're going to get. We're very, very good at all of that. Okay. And I can tell you guys that if I need to go into more depth to help you all kind of explain and understand some of these things, I can do that. Dr. Mike will do a huge amount more talking about those things when you get into exercise physiology. I just want to introduce enough of these concepts so that you can have a general understanding. And then, as you will see later on today, when we start talking about adaptations to resistance training, some of these things are going to change. The way the brain communicates with the muscles is going to become a little bit more efficient. The way that we can turn on more and more of the muscle that we already have is going to become more efficient. And so I just want to give you guys enough of a flavor of how all of that works so that when we talk about adaptations to training, that will make some sense to you. Okay. So we're going to start today by talking about this relationship between contraction velocity and force production. Okay. So what I want all of you guys to think about is think about a time you had to do something really, really fast. Okay. And think about how much force you were able to produce when you were going really, really fast. Okay. And so there exists a relationship, and it is rooted in the way that cross bridges are formed and the way the cross bridge cycle takes place. There's a relationship between how fast you can make a muscle contract and the amount of force that you okay? And so the very general way to describe this relationship is by what you see in the graph up here on the top left. And so these are some data that I pulled from a research article that was published in 1950. This is a concept that we could do in lab if we wanted to. If you take exercise physiology lab with Dr. Pereira, then you guys will make your own curves. Everybody has this own individual relationship where basically when the velocity of contraction is very, very high, the amount of force that you can produce from your muscles is going to be very, very low. And as the force of contraction increases, or if you want to increase the force of contraction, then you've got to slow down. Okay. You've got to make the contraction go slower and slower. And so imagine this in your own life. If I gave you, let's just say, if I had my cup here, which I have Diet Mountain Dew in, but let's imagine that I wanted to do something and I wanted to move this very, very fast because it doesn't weigh much. I could go very, very quick. Okay. I'm now looking around my daughter's playroom looking for something, but if I had something that rather than having sort of being made out of plastic and this was made out of lead. And so let's say it weighed like 20 pounds or something, and I wanted to move it around because it weighs more, it would be more difficult for me to move it at a particular speed. Okay. And so when we normally do an exercise in class where I have people, we bring out a bunch of weights, either I will do it or we'll get a volunteer and we'll have you do like a curl exercise. And we give you 5 pounds and we say, go as fast as you possibly can. And we try to time that, like how long does it take to do 5 or 6 repetitions? And then we slowly increase the amount of weight that we give the person until we get up to where, it's very, very heavy for them and they're really, really struggling and going really, really slowly. Okay. So you probably can envision a situation like that if you were either at your apartment there, if you have some weights there, you could try that, or if you were going to go to the gym or do something. But the more weight you want to lift, which is going to require more force, the slower you're going to be able to move things. And that's the general way to try to kind of think about how this relationship is going to work. Okay. So on this particular relationship, I know we started talking about the different kinds of contractions at the very end last time. We need to understand the three types of muscle contractions because each of them are going to behave a little bit differently in relation to how velocity is going to affect force production. Okay. So the graph that you're seeing right here, this is going to illustrate the relationship for a concentric muscle contraction. So a contraction where if I'm doing a bicep curl, where my bicep here is actively shortening. Okay. So in a concentric contraction, to get more force or to lift more weight, you're going to go slower. Okay. If we were to look on this graph, an isometric contraction where I'm holding something steady, okay, or I'm pushing against something and I can't move it, and so the muscle is not actively changing length, that occurs on this graph. It occurs right here, okay? It occurs where the line illustrating the kind of relationship between force and velocity would intersect with the axis showing velocity because there's no movement with isometric contractions, there's no velocity. And so we're going to look here at a zero velocity contraction. And what you can see is that at a zero velocity contraction, that's going to yield us the highest amount of force, okay, in comparison to any of our concentric contractions. And so because we don't do a lot of isometric contractions in our everyday life, you may not think about this or have a lot of kind of experience with this, but in an experimental setting, we should be able to elicit more force from your muscle under an isometric contraction than we could do if you were doing any kind of a concentric contraction, no matter what the velocity is. Okay. And so if you think about this, if you've ever lifted weights, I always like to think about like if you're doing squats or something, you can unrack if somebody would help you, and you can hold more weight on your back to try to do a squat. Like you can hold that position with more weight than you can ever hope to kind of go down and come back up with. Okay. That's an idea of kind of how we get more force out of isometric contractions than we do from concentric contractions. Okay. So we'll talk a little bit now about kind of why this is going to be the case. What's the physiology that means it has to look like this? And then we'll talk about what happens during eccentric contractions because it's even stranger than what's going to go on here. Okay. So remember that force generated during a contraction is directly related to the number of cross bridges that are going to be engaged at any moment in time. Okay. And so, by some level of reasoning with all of that, then what that's going to tell us is that under isometric contraction conditions or slow concentric contraction conditions, we're getting more force. So, therefore, we must be able to engage more cross bridges than what we are able to engage here when we're doing things very, very fast. Okay. And indeed, that is why this relationship looks the way that it does. So, as the velocity of contraction increases, okay, the number of times that we have to, and I'm going to back up here on the screen, the number of times that we have to cycle through the cross bridge cycle, the number of times that we have to attach and form a cross bridge, get a power stroke, bring in ATP, and break it off, and then recock the myosin head and reattach and start over again. The number of times it has to bind, move, let go, bind, move, let go is going to happen faster and faster and faster and more often and more often and more often. And so, because of that, if we were to measure the number of actin and myosin cross bridges that are formed at any sort of instant in time when you're going very fast, there's going to be fewer of them that are engaged and making a cross bridge, and more of them that are at some state of we've broken off or we're trying to reattach or we're trying to kind of recock the myosin head. Okay. So velocity influences force production by influencing the interactions of actin and myosin. So to go fast, you've got to break those cross bridges apart. You have to use lots and lots of energy, okay? And that means that we're gonna get less force production. Okay. So when you do things fast, it costs more, you get less force and it costs you more energy. So that's going to be kind of a very inefficient use of getting force and from an energy production standpoint. Okay. Now, with eccentric contractions, and this is one that we usually try to illustrate in class, that everybody really enjoys, because we will oftentimes find the person that we think has the biggest muscles in class, and we'll have them do a competition with someone that we think has significantly smaller muscles than they do in class. But if we look at the eccentric portion of this relationship, so what I just showed you guys in the previous slide is the concentric side over here. And I want you to notice that the axes have been flipped on this graph in comparison to the graph on the slide before. Okay, so now velocity is going down here on the x-axis, and force is here on the y-axis. And so on the right side of this graph, where we're doing a shortening or a concentric contraction, this point right here where the blue line intersects, that's zero velocity. So this is where our isometric contraction takes place. And then as we move to the right along that axis, that means we're increasing velocity in what this graph is going to call the positive direction. And so that means that velocity is going up, but the muscle is shortening. Okay. And so because that this is this nice parabolic relationship, it doesn't really matter how we orient the axis, the relationship is going to have the same shape to it. So on the eccentric side, here we have zero velocity, so we have an isometric contraction. And then this is going to demonstrate as we move left from that intersection, increasing velocity in the negative direction, or increasing velocity as the muscle is actively lengthening. So this is, I'm doing the letting down portion of a bicep curl, or this is me, I'm doing a squat, and this is the part where I'm sinking down into the squat. Okay. So what you will note is that as velocity goes up during eccentric contractions, force production does not go down. It actually increases a little bit, and then it's going to mostly level off as we go faster and faster. Okay. So we talk about this relationship, we talk about eccentric contractions in general as being that force is independent of velocity. Okay. Force is independent of velocity. And the reason that's going to be the case is that during eccentric contractions, we can engage a cross bridge, and we, for the most part, don't ever have to break that cross bridge apart. Okay. And so because of that, we maintain force production, and doing eccentric contractions don't cost us very much energy. Okay. Now, you may say, Dr. Black, that's great. You're engaging these cross bridges, that's going to get us force, but shouldn't that only get us as much force as you would see like in a very slow concentric contraction when most of them are engaged, or in an isometric contraction when most of them are engaged? And I would say, yes, absolutely, that is what you would think would happen. But we also have to remember that in your skeletal muscle is going to be connective tissue. So, and then there's also going to be the muscle connecting to tendons and ligaments. And so connective tissue and your tendons and ligaments act like rubber bands. Okay. They're elastic, so we can stretch them, and then they want to go back to their original state. That's why they're going to be called elastic. Okay. And so we're going to engage our cross bridges. That gets us a certain amount of force. But then as we stretch the muscle out, as we stretch the ligaments and tendons, as we stretch the connective tissue that surrounds the individual muscle fibers and the muscle fascicles and things, that's going to store a level of elastic energy that is going to resist against the weight moving in that particular direction. And so that means you get force from stored elastic energy plus force from the actual interaction of your cross bridges. Okay. And that's why you will always be able to lower down more weight than you can ever hope to pick up. We will do that, and we can do it in class on Monday. Assuming we get to come to class, we can do a demonstration with this. But I can give you, let's say the most weight you can pick up when you do a curl is 20 pounds. I can probably give you 25 pounds here, and you can lower it down easily without kind of dropping it without any problems. Okay. But you can never pick that 25-pound weight up doing a regular curl. And that's because you've got that extra stored elastic energy. Okay. Additionally, because eccentric contractions don't have to undergo the cross bridge cycle in the way that concentric contractions do, what you find is that they don't use nearly as much energy. This is why, and we did a little bit of an illustration of this with Bria in class on Monday. This is why metabolically it feels easier to walk downstairs. This is why it always feels easier to, if you're jogging, to go jog down a hill rather than on level ground or up a hill. Because when you're running, when you're jogging, when you're walking, the primary muscles, your quads and your glutes and things, when you're going down the hill, they are doing mostly eccentric contractions, rather than having to do concentric contractions when you're running on level ground or up a hill. And so because of that, then they can generate plenty of force, but it doesn't cost nearly as much energy. And that's why it's much easier, and it feels much easier to run downhill, because it actually is. It costs you less metabolism or less ATP to do that. Okay. So of the things that we do and that we cover in class, this relationship and then kind of the way the cross bridge cycle fits into this is probably the most conceptually complicated thing that we will cover, I think, for the entirety of class. Okay. So I know we're not really in a great situation to kind of quiz each other about all of this, but we'll try, if we can get back in class on Monday, to do a couple of demonstrations, so that you guys can visualize what this looks like, because that always seems to really help with everyone, is to try to visualize this. And then we'll kind of go back over it, and I'll maybe give you guys a take-home assignment on what this is going to be, to try to help you kind of keep thinking your way through it, so that hopefully it sinks in and it makes sense. Okay. All right. So now, and I'm going to pull everybody up at least on this. So the next piece of everything that we're going to talk about in class is probably going to be some of the most interesting, and the stuff that some people in class are going to be the most excited about. Okay. And that's going to be resistance training. So I like to start the resistance training portion of things by doing this. So if you've ever done resistance training, if you've ever lifted weights or done push-ups or done sit-ups or something like that, give me a thumbs up with your hand, or flash your camera at me, whatever you feel the most comfortable with. So, okay, I'm getting a few. There we go. Now I'm getting almost everybody. Okay. Excellent. I was worried that a bunch of y'all had decided that you had your things on, and you just like gone away because I was boring you to death. But okay. Excellent. So
I don't know how to do the thumbs up.
No, that's okay. Thank you, Kelly. So I'm just going to pick somebody in some ways kind of at random here. Katie. Oh, hi. Okay, awesome. You've turned your camera on, so you don't have to. So my question is, Katie, would you mind sharing with us, like the last time you went to lift weights, what did you do and why did you do it?
I used pretty low weights.
Okay.
Well, I feel like I'm not really a good example. Like I wasn't really
That's
allowed
okay.
to use heavy weights.
Okay. Any kind of an example is a good example. Is at least is going to illustrate kind of our point behind this. Why did you go lift weights? What were you hoping to gain by all of that?
To gain muscle, because muscle is better for your like BMR than non-muscle tissue.
Absolutely, it is. The more muscle you have, the more I get to eat, right? That's the kind of the general way that I take those
Yeah.
things.
I'm making
Okay.
breakfast right now, so
You wanted to build muscle. Did you want to do anything else? Uh-oh, I have a guest sneaking into, he has escaped from where he's supposed to be, but here's one of my basset hounds sneaking in. So Truman has come to see me, everybody. If you guys maybe can hear, his brother Gus is downstairs barking. This all means my wife is gone. She's left to go get the things. Truman knows how to open the baby gates because he's way too smart for his own good. So, Katie, did you have any other things like you just want to get some muscle? Do you have any other like goals for things when you wanted to go do resistance training?
I'd like it to look like I lift weights.
You'd like it to look like you lift weights. Can you be more specific on what you mean by all of that? I
Like,
think I know, but I don't want to make an assumption.
have
So
toned arms.
you want to
and-
have toned arms. Okay. Unbeknownst to Katie and to all of the rest of you, Katie has just used the one word that probably sets me into like a fit of rage more than any other word in the history of bro science, which is tone, which is a very commonly used kind of thing. And that's okay, Katie. We would talk about it at some point anyway. So I appreciate you saying it. So we will talk about it as we move through here kind of today, and then we'll talk about what it means. I know what you mean by being toned. Lots of other people probably don't use the word in the most correct fashion, but so you want to look like, I want to look like I've got these toned muscles, right? I want to walk around and I've got like these traps and shoulders and all this, I'm speaking maybe for myself, not so much for Katie. In the midst of this, she may want, those kinds of things. Others. Okay. Thank you, Katie. We'll pick someone else that I think had done something. So, Cade. Cade, are you there? Can you hear me? Cade has unmuted himself, but I don't know. Cade, if you can hear me, the last time you went to lift weights, what were you hoping to gain from that? Nope. Okay. We've lost Cade. Oh, maybe he's typing in the chat. More muscle. Okay. Anybody hoping to get stronger? It's very common we want to get muscle. Anybody hoping when you go lift weights, you want to be stronger?
Yes, for me, I'd say I like to play golf, so be able to hit the ball farther.
Okay. Zach wants to lift weights so he can hit the golf ball farther. Absolutely, right? If you ever played a sport, maybe you thought like, I want to jump higher, I want to run faster, I want to do some of these things. Okay. So these are the goals that people tend to have when they do resistance training. And my guess is that all of you that have done something had something like that in your mind when you were thinking about it. Like, I'm going to go and I'm going to do this. And I am hoping that this will let me have bigger muscles, or we'll say more defined muscles rather than more toned muscles and those kinds of things. Or, right, like I want to be able to bench press more than this other dude that I see every Monday, whatever it's going to be. So I can hit a golf ball farther, all of those kinds of things. All right. So that's absolutely right, guys. That's the goal of resistance training. Okay. We want to get stronger, and we would like to, hopefully, for most people, have at least somewhat larger muscles. Okay. And as you get to be my age, then what you really are thinking about is, man, I'm losing muscle. Can I please just hang on to whatever muscle that I have? I've lost all designs on if I'd known this is what 42 was going to be, I would have like walked around like no shirt from the time I was like 15 until about 24 and just been like, here, look, I have muscles. I'm never going to have them again. Kind of here's what's happening in the midst of that. It's a cautionary tale, everybody. So my next question is, and I'll just pick someone else. Let's see. Haley. How big do you think you can make your muscles, Haley? How much bigger than your muscles are currently do you think you could make them?
Me, right?
Yes, you.
Okay. I mean, I think you can make them as big as you want as long as you're like feeding your body.
I can make them as big, so I could be the Rock as long as I.
Okay,
As
not
long as I.
necessarily.
Okay.
I think that if you're feeding your body enough and giving your body enough like nutrition and protein and stuff like that, and you're able to build your muscle up, get as big as you want, like to
Okay.
your.
Okay. No, that's a great answer. Portia, do you agree with Haley? Do you think that's the most correct answer? Because I will say that like nutrition and stuff is a very, very important part of what sort of we can expect from a gain standpoint. Do you think I can be as big as I want, or that Haley could be as big as she could want, Portia?
I don't think you can be as big as you want just because we're all genetically designed with a certain type, like amount of muscle fibers and whatnot. But I
Okay.
think you can increase. I think everyone does have the like power with nutrition, with proper nutrition and exercise to increase significantly more than they think.
Okay. Okay. That's a good answer. If we had to put a number on it from like a weight gain standpoint, um, Susie, how much weight do you think like a regular person could gain? Like if you were to go do perfect nutrition, perfect resistance training, like how much weight do you think you could gain by adding muscle? Nope. Susie? Okay, we'll try someone else. Hallie, you were next to her on my screen. Hallie, what do you think?
Can you repeat the question one more time?
Absolutely. How much, like, how much weight do you think a regular person or that you could gain if you had like really, really perfect nutrition and like the most perfect resistance training, like weight training regime? Do you think you could gain 5 pounds, 10 pounds, 50 pounds? Like, what do you think is a reasonable amount?
I feel like it'd be around 40 pounds, but I
Okay.
feel like it's more per pound per muscle fiber.
Okay. Okay.
Does that also depend on like height too? Because like people that are shorter are able to, I guess you could say, look more. I guess I don't want to use the word tone because I know,
That's
but
good, Zach. See, we're learning. Let's not use the word tone.
look
Define
more filled out, I guess.
more filled out. Okay. So I feel attacked as a somewhat shorter. I guess I'm like right at the average for adult men in the US, but those kinds of things. So some of this is going to be genetic, right? And some of it is going to be related to nutrition. Appearance is going to also be kind of genetically controlled. Some of it's about like body size and frame, but there's also going to be kind of anatomical differences, right? And some people just have muscles that look bigger or look more defined for a host of reasons than others. Um, so I like to start this section of things by asking you guys all of these questions like this because I think it's really important that we go into this with an idea of kind of here's what people tend to think resistance training may be. Here's what people tend to think is how much bigger their muscles can get, how much weight they might be able to gain, how much more they might be able to lift if they just train in a particular way. Okay. Because resistance training is one of the most common forms of exercise. It is, in my mind, one of the most commonly kind of misperformed types of exercise. And a lot of that misperformance is going to be wrapped up in what I think of as kind of two sides of the same coin of a myth where women tend to lift in one way very often, although it's becoming much less so, lift in one way because they're worried their muscles are going to get too big, right? Or they may look too bulky or something like all of that. And then guys lift in a certain way, maybe not you guys, but like some of the bros lift in a certain way because they overestimate how big their muscles are going to be able to get and overestimate how much stronger they're going to. And they think if they just do these kind of one certain things that it's going to magically do all of this. And so all of the things that you guys mentioned, right? About I'm going to lift weights because I would like to have bigger muscles. I'm going to lift weights because I want to be stronger, either just for the sake of being stronger or because there's going to have some transfer to a sport or something that I care about, right? Or I want more defined looking muscles and those kinds of things. All of that stuff is 100% true. Okay. Those are absolutely the right ideas. Those are absolutely things that resistance training 100% can do. Okay. And so Hallie said she thought maybe you could gain 40 pounds in the midst of that. And I would say that some people might be able to. There's going to be a lot of other things that go into it. But an average person probably not going to be able to gain that much sort of in just from a muscle standpoint. But we'll talk a little bit more about that as we kind of go along here. Okay, so I'm gonna go back to the PowerPoints from my end of things. All right, so we're gonna talk about in this section, what are some of the physiological things that are going to change? And then once we've done some of this, we're not going to talk about until next week. We're not going to talk about like what's the optimum way that we should train, how many days per week, roughly how many sets, how many repetitions, right? How much weight do we need to be lifting during each thing, and kind of what are the differences and all of that going to be. Today is going to be much more focused very, very simply on what changes and kind of to what extent is it going to be able to change. Okay. All right. So I'm going to kind of give you guys the big broad picture here, and then we'll dig down into each one of these a little bit farther. Okay. So the primary thing, as you guys mentioned, that's going to happen when I do resistance training is that we can increase muscle mass. Okay. So your muscles get bigger, and the muscles get bigger because the size of individual fibers is going to increase. Okay. I can't remember if we talked about this before or not, but I will tell you guys now. You all were born with all of the muscle fibers that you're ever going to have in your body. It blows my mind all the time. Okay. You're born, and just think about, like, I think about how small my daughter is, but she has the same number of muscle fibers at 2 as she's going to have when she's 20. Okay. The fibers will grow some with us, but we think that the number of fibers that you have is going to be one of the things that may put a genetic limit on how big your muscles can get. Okay. A person that has, before they start lifting, many, many small muscle fibers might be able to have a larger increase than somebody that already doesn't have as many fibers, and their kind of untrained fiber size is a little bit bigger. So each individual fiber gets bigger. It gets bigger by adding actin and myosin, by adding sarcomeres and myofibrils inside the muscle fiber. And so it gets bigger. And that's going to be one of the reasons that we get stronger. Okay. More actin and myosin, more cross bridges, therefore more force. Okay. The other thing that happens outside of muscle size is that we're going to get stronger. And as I said, you're going to get a little bit stronger because of the increase in actin and myosin, but we're also going to get stronger because of these next two ideas. Okay. Because of an increased ability to turn on or recruit the motor units that are already in your muscles. Okay. For those of you guys that aren't used to doing a particular movement, maybe you don't normally do squats or something like that, or you don't normally do a bench press. If we ask you to do that, when you first start out, your motor cortex does not understand the proper kind of motor plan or movement pattern to efficiently perform that particular task. And so when it does those things, you are very likely not going to be able to turn on or recruit all of the motor units in the muscles that you're using. When you're untrained at something, you have a reserve. You have muscle that doesn't ever get turned on during that exercise because the brain hasn't learned how to do that yet. And so as you resistance train or as you practice, whatever it might be, okay, and that can be things that you don't even think of, like learning to play the guitar or a musical instrument or doing ballet dance or these things that are not just I'm lifting as much weight as I can, but you're going to learn how to recruit and turn on those muscles in a more coordinated manner and develop a proper motor plan, but you're also going to be able to increase the total number that you can turn on. Okay. And so that means that early on, you guys will see early on in resistance training, you're going to get stronger very, very quickly. You're going to get stronger well before your muscles are ever going to get bigger. And so the reason that you're getting stronger is because of these changes in recruitment. We call those neural adaptations. And I'll show you guys a couple of slides about kind of some of the particulars of kind of how and why we think that's happening a little bit later on. But that's the big kind of thing here. Bigger muscles, improve strength. Bigger muscles because of more actin and myosin, improve strength because of 1, bigger muscles, and 2, better recruitment. Additionally, and these are going to be things that we will talk about later on in class and they become particularly important with aging and things, but resistance training also is going to stress ligaments and tendons and your bones. And so if you are consistently resistance training and consistently stressing those, your tendons they have more collagen in them, they become stronger and more elastic. Your bones are going to deposit more calcium in them, and your bones are going to become larger and stronger as well. And these are going to be things that can prevent us from having injuries to those tendons and ligaments, okay? And keeping bones strong and healthy is going to be one of the ways that we can limit fractures when you get old and you fall down. It can be one of our ways to try to combat oh God, I've gone a complete osteoporosis is through doing all of this. The other thing that happens, and when we get into talking about cardiovascular disease and diabetes, we don't often think of that resistance training is also really good for cardiovascular disease, and it's really good for type 2 diabetes because 1, the exercise itself, performing it is going to have positive effects, but also having more muscle mass is also going to have a positive effect on altering our blood cholesterol levels. It's going to lower LDL cholesterol and increase HDL cholesterol, which means we're at less risk of developing atherosclerosis and high blood pressure and coronary artery disease. And having more muscle and doing contractions is going to improve our insulin sensitivity, which is one of the things that tends to become a problem as type 2 diabetes develops. So we can use resistance training, we can use an increase in muscle mass to help us combat cardiovascular disease and type 2 diabetes. And so all of you guys that are doing these things now, that's great. I would encourage you to continue doing them because it's going to have positive outcomes on this throughout the rest of your life. Okay, so now comes the really fun part, okay? It's going to get into this idea of how strong can you become, okay? And how big can your muscles eventually get to be, all right? So for most people, if we were to look on average, an average person, which I don't want to make any suggestions that any of you guys are average, but if we were to just randomly pick one of you guys and we were to train you for the rest of this semester and into the summer, so for about 3 to 6 months, in general, you could probably increase your strength in a particular lift, okay? Squatting, curls, power cleans, whatever it's going to be, somewhere between maybe 25 to 100%, okay? Kelly, you can't see my screen. Is anybody else having the same problem?
I can see it.
Okay.
Oh, I don't see the PowerPoint. I just see like you.
You just see me?
Yeah. I don't know if there's something. Okay, well,
Other folks, are y'all seeing the PowerPoint or are you just seeing me? I just completely minimized my Zoom thing.
okay, it's probably just me. Like I'm super bad with the computer, so
That's okay.
it's something that I have to figure out. Sorry.
Okay. No, that's okay. I'm sorry, Kelly. I wish I knew what to tell you. That's a new one for me because it seems like other folks are able to see. So what I'm going to do, just to see if it helps, I'm going to stop sharing, and then I'm going to reshare. What about now? Did that fix anything, Kelly?
Yes, I see it now. Thank you.
Okay, perfect. Awesome. I have
Sorry.
no idea what was going on, but that's okay. We'll keep rocking and rolling. So the average person, okay, the average of you guys, probably somewhere between 25% and 100%. And so that means if maybe you could lift 100 pounds right now on a given lift, with 3 to 6 months of training, you might be able to lift anywhere between 125 and 200 pounds. Okay. And so that's a big range. All right. And there's a lot of things that are going to affect that range. And we'll talk a little bit about what some of those things are. Okay. So the really cool thing to me about all of this is that the changes in strength are going to be relatively similar between men and women, old people and young people. Okay. The difference is going to come in to what is your initial level of strength. And we have to be sure that we express how much stronger you're getting relative to how much you can lift initially. So let's just say we have a stronger person, right? We have a guy who can squat 200 pounds, and then he is going to increase that to 250 pounds. That's a 25% increase. We have a woman who can lift 100 pounds, and she increases it to 125. That's the same 25% increase, even though in an absolute sense, the guy's gone up 50 pounds and the woman has gone up 25 pounds. For, I don't know, until sort of the mid 90s, it never occurred to exercise physiologists to try to express changes in strength in things relative to the initial strength. And so we thought for a while that women were unable to increase their strength to the same extent as men. And as it turns out, we were totally wrong. And it was just a matter of that in general, women are a little smaller, they have a little bit less muscle, and so therefore they're going to have kind of lower starting values. And so when we normalize that out, then they're about the same. Same thing in older people. As you get older, you tend to lose muscle mass, you tend to lose some strength. And so then if you just normalize how much an older person can increase theirs compared to what a young person, it all tends to be about the same. This is great because it is going to tell us that it doesn't matter what your sex is, you can get stronger and you can generally make your muscles get bigger, and it's all going to be relatively similar. Okay, so everybody can get the benefits from that. And if you get older and you start losing things, if you'll either take the training back up or you'll continue the training, then you can recover some of that strength that you've lost or some of that muscle mass that you've lost. And so that's the great thing about almost all kinds of exercise, but especially resistance training, is that it works in everyone. Okay, regardless of age, regardless of sex, and those things. And that can be a really, really positive thing to try to encourage people to do it. Okay. So we talked about the neural adaptations. We talked about the contractile adaptations. So when you get stronger, part of it is going to be increases in ability to recruit. Those are neural adaptations. Those tend to occur first. And then over time, you're going to see an increase in muscle size, which we also call contractile protein adaptation. So you're just going to have these noticeably bigger muscles. All right. When muscles get bigger, we often refer to that as hypertrophy. So we will say that your muscles have hypertrophy, which just means they've gotten bigger. The converse of hypertrophy is atrophy. And so when you have atrophy, your muscles are going to get smaller. So in general, aging tends to lead to atrophy, inactivity tends to lead to atrophy, space flight leads to atrophy. If you have to put a muscle in a cast or something, or you're bedridden for a while, that leads to atrophy. Whereas for the most part, resistance training will get you hypertrophy. Also, taking steroids will get you hypertrophy. We'll talk about that in one of our bro science days. Okay. All right. So here is here's a what looks like a piece of steak. This is an MRI of a cross section of a person's. This is taken at about mid thigh. And so what you see here I don't know. Can y'all see the cursor that I'm moving around? But if I'm moving this with the cursor that you guys can see in the middle here, this kind of light colored dot, that's bone marrow. So this is the person's femur right here. This is a left leg. We're looking up through the person's feet at their legs. So the vastus lateralis is out here. We have the vastus intermedius. Here's the vastus medialis. There's the rectus femoris. Here's going to be the femoral artery in the femoral brain. Your hamstrings are down here. So this is a person that did 6 months of resistance training. And you can see how in 3 months they got a lot bigger. And then in 6 months they got bigger, but not nearly so much. Okay. This particular person was a guy that had a spinal cord injury that we trained in our lab as part of my PhD program. And so this amount of increase in muscle size was about 100%. So his muscles were like double. His muscles got to be double what you see here at 6 months. This leg was not even as big as a normal person, kind of a normal average adult, what their leg is. And so initial muscle size matters. Okay. And it's going to have some effects on your ability to kind of increase muscle size. But that's kind of how we're going to, do I not have that thing in here? We talk about this a little bit. Okay. So I need to, I apologize that I don't have the actual numbers written here. For you guys, if you can increase your strength, say 25 to 100%, this is 100% increase in muscle size. The vast majority of you all can get nowhere close to this. Okay. An average person is going to be in a particular muscle somewhere between maybe 10 and 20% is the average amount that you can increase your muscles. Okay. To put that into context a little bit, remember that Hallie said that maybe you could add 40 pounds of weight by training. If we took a person that weighed 150 pounds, let's just say, okay, we increased every muscle in their body. Okay, every muscle in their body, 15%. You're a 150-pound person, 15% body fat was the numbers that we used. You increase every muscle in their body by 15%, which you could notice they would gain 8 pounds. Okay, 8 pounds. It would be noticeable, it is real, and it is important. They would be a lot stronger. They would be better from a type 2 diabetes risk, from a cardiovascular disease risk, okay? But it's important to remember and just kind of keep some of these things in line that most of us are not going to be able to increase our muscles to what we might think of as just this massive, massive, massive degree, okay? We can all make them go up. We can all make them more defined and more noticeable. But also we're going to have to appreciate that if you want to add, so you add 8 pounds of muscle, but what if you also are adding, 10 pounds of fat and connective tissue and things on top of all of that? That may be where we're getting some of this extra. So if you hear about, oh, there's these football players or basketball players, or you have these athletes and it's the off season and they put on 30 pounds of muscle in a single 3-month off season, that's one of two things. One, that's either steroids, or two, they're just full of shit. Okay. That's just not a thing that can happen. And so I say all of this because one of the things that we have had to fight through the years, and we do less so now, I think culturally things are beginning to change, is that women have this thought that I don't want to lift heavier weights because I'm worried that I'm going to gain all of this muscle and somehow I may not appear, feminine, right? I may look manly or have these great big muscles or be bulky or whatever that you have heard, and you hear a lot of those kinds of things. And the vast majority of that stuff, it's just 100% not true. Okay. And even for women that are on the high end of responders and that can gain quite a bit of muscle, then I think we're beginning to make some progress that's good. Having strength as a woman is good. Having more muscle is good because there's these health benefits, there's these functional benefits and things. And so I think that's going to be a good thing. But I promise you that if we were at school and we could go over to the Huff, and maybe some of y'all have done this, but I guarantee you we could walk over there and we could find some ladies that were doing like curls with 5-pound dumbbells. They would do like curls, and then they would do some shoulder press, and they would do some tricep kickbacks, right? And they're going to do a little bit of plank and some other things. And you ask them what they're doing, and they're going to say, oh, well, I'm lifting these very light weights because I want my muscles to be toned. I don't want to appear to have these large muscles or whatever. And all that I would argue with them is that when they're doing that, they're just in there spinning their wheels. They're not actually getting any stronger. They're not lifting enough weight to gain any muscle mass, and they're not really expending very many calories. And so I'm just not 100% sure like what they've accomplished other than they've been to the gym, which is not a bad thing, but we can do this stuff better. On the flip side, the guys that may think like, bro, I'm gonna be as big as I want. I'm gonna put on 50 pounds. I'm gonna look like The Rock or whatever. I'm gonna go be a stunt man, right, in movies and all of this stuff, or I'm gonna be the best. I'm gonna go play football now because I've done this. Also, probably not the case. Okay, probably not the case. It's a little bit different if you're kind of in the kind of immediately post-puberty regions. When you're still growing, you can see folks that are in high school, you may be able to have gained 30 or 40 pounds from one year to the next. And a lot of that being muscle, both guys and girls, but some of that is all related to growth and development. You can't take a 25-year-old for the most part and think that they're going to kind of massively increase their muscle mass, to this huge extent. If people do, then they're probably taking steroids. Okay. All right. So questions about any of that stuff, guys? I'll get off my soapbox now. Okay. So what I'm going to do is let's take a break. I'm going to stop sharing, and I'm going to pause the recording, turn back on. Okay. So when we're thinking about hypertrophy, remember that we have a certain amount of muscle fibers. Here's what's going to happen. Here's our muscle fibers in our untrained person. Then we do, say, 12 weeks or 16 weeks of resistance training. And then as their muscle gets bigger, it's going to look like this, okay? That you had a fiber or you here, and then it's going to get bigger. So here's one fiber with individual myofibrils in it. And then here is the fiber has gotten bigger and each of the myofibrils has gotten bigger. And so we think this is the primary way that humans are going to make their muscles bigger. I'll mention a concept called hyperplasia, which is one fiber turning into two fibers, which we do see in some animal models and that we think may be promoted by people taking like testosterone or different kinds of steroid hormones. But we think it's very, very unlikely to occur under regular circumstances in normal people. Okay. So we talked about this top part a little bit already. The other piece of this that I want to make sure that I hit on, people oftentimes have questions on, is does the type of muscle fibers that you have, so are they type 1, are they type 2A, are they type 2X, like your relative percentages, does that play some role in the amount of hypertrophy that we can see? Like, are some of those fibers more prone to being able to increase in size than others? And the answer to this a little bit is we don't know. It's hard for us to know for sure, because what we do know is that the more that you use fibers, the larger they tend to get. And so there is a thought process that when we look at things, we tend to see more hypertrophy in type 2A and type 2X muscle fibers than we do in type 1. So the fast twitch fibers seem to get bigger than slow twitch fibers do. But the problem, or the thing that we don't fully kind of have a way to separate from this, is that we use the type 1 fibers. You use your slow twitch fibers much more often in everyday activities that may not look like resistance training than you do your 2As and your 2Xs. And so it's possible that everyday activities, at least when you first started doing them, were sufficiently stressful to cause the type 1 fibers to get a little bit bigger. And they're already in some ways kind of as big as they're going to get. And that's why they don't seem to hypertrophy as much, that they have the same potential to hypertrophy. It's just that nobody is generally so untrained that their ones are going to be kind of really small. There's some debate about that. We don't really know. because there's some other things that tend to be associated with people that have kind of different fiber types. Okay. What we also will see though is when you are active, when you do resistance training, you will convert type 2X fibers into type 2A fibers. This is the same adaptation that happens with walking or running or cycling. So any kind of physical activity is going to shift 2X fibers to become 2A fibers, which is going to have benefits from an endurance standpoint. Okay. So that's going to happen. So another idea that we need to talk about, which I think is kind of a thing that you may see in the gym all the time, if and when you go, is this idea of something called transient hypertrophy. So you guys don't have to sort of signal if you've had this experience, but my guess is that many of you have. If not, if you've ever been to a gym, you may have seen people that were experiencing this and kind of looking at themselves and admiring themselves over it. So when you do a resistance training workout, okay, you are going to see this immediate increase in the size of the muscles that you were using to perform a particular lift or that you were using during that particular workout. Okay. I'm going to go and I'm going to do some curls and then I'm going to do some shoulder press. And magically, right after I've finished doing that, it feels like and it will look like my bicep has gotten bigger or my deltoids have gotten bigger, or I did a bunch of crunches and now it looks like that my abdominal muscles are bigger or more pronounced or something in that way. Okay. This is the idea of transient hypertrophy. And it's primarily the result of an increase in fluid in those muscles. Okay. And so you get fluid being driven into the muscles. It's going to be fluid from your blood. So it's plasma, water leaving the blood, and then water coming out of interstitial space and being driven into the cells because of the increases in blood pressure and because of the metabolic shifts that are going on in the muscles is going to want to draw some of that water in. And so it's real, like your muscles are bigger, right? They look more swollen, they appear larger because they are, but it's all water. Okay. And then if you wait a couple of hours, then the water's going to all go back to normal. Hydrostatic and oncotic pressure are going to normalize, and that water is going to get released out of your muscles and it's going to go away. Okay. A very bro-ish way to refer to transient hypertrophy is a pump, right? I went and I got a pump and my muscles are going to feel all like big and swollen. And here I am. And so I'm going to look at myself in the mirror and be like, oh, look at how good my workout was and all these kinds of things. And then a couple hours later, you return back down to a more normal size. But that's what this idea of transient hypertrophy is. It's caused by a fluid shift as opposed to some actual change in the proteins that are going to be inside the muscles. Okay. So in order to make muscles grow, we need to make more actin and more myosin and some of the structural proteins and things that are going to also anchor sarcomeres and myofibrils. And that is going to be controlled by a process called protein balance. Okay. My dad, the football coach, used to always tell me, like, every day in your life, you're either getting better or you're getting worse. You're never staying the same. And I take that like your muscles are always either getting bigger or they're getting smaller. So the protein in your muscle is always in a constant state of flux, where in some muscles you're making new protein and in other muscles you're breaking down the protein so you can send those amino acids elsewhere. Okay. So there's this constant turnover in the push and pull between the idea of synthesis or making new protein or degrading the protein that we currently have. Okay. So to make your muscles get bigger, to experience hypertrophy, you need to be in what we call a positive protein balance. So we need synthesis of new proteins to predominate over degradation over some sustained period of time, over several weeks or several months. That's going to lead to increases in muscle size. Atrophy, on the other hand, is the idea of a negative protein balance. So you're going to have where degradation is going to predominate over synthesis for some prolonged period of time, and that's going to lead to a shrinking of your muscles. So to understand then how muscles get bigger, we need to understand how protein balance is going to be regulated. So we need to figure out what can we do, both from a lifting weight standpoint or from a nutrition standpoint, to tip the scales in favor of synthesis and away from degradation. And so that may mean make synthesis go up more, or it may mean to inhibit the idea of degradation. And so in a very general sense, protein balance is regulated by a lot of complex factors. Some of them are going to be hormones, things like testosterone, growth hormone, insulin-like growth factor 1. We call these very typically anabolic hormones. Things that drive protein synthesis are anabolic. There are some other growth factors and things that are going to be in your muscles that we want to get turned on. There's some signaling pathways, AMP kinase, something called mTOR, that are some of the cellular pathways that we know that exercise seems to activate. And they're going to activate them independent of hormones. And so if we can activate those, that's going to kind of lead to an increase in protein synthesis. We also know that consumption of what are called branch chain amino acids, so sort of essential proteins, especially a protein called leucine, or an amino acid called leucine, I'm sorry, that ingestion of protein also seems to drive synthesis. Because when you're eating more protein, muscles are not the only tissue in your body that needs the protein. And so if you're providing it in the diet, then that's going to drive synthesis not only in your muscles, but in some other tissues. And it's going to also inhibit degradation of protein from your muscles in case, other tissues in your bodies may need those amino acids. The body will try to take it out of muscle to give it to your liver or your kidneys or your brain or your heart or someplace like that if it needs it. Okay. So by eating more proteins, especially these branch chain amino acids, then you're going to provide those building blocks that both muscles and other tissues may need without having to degrade the stuff that's in the muscles. Okay, so with resistance training, we know that we're going to generally be able to get hypertrophy, so it probably increases expression of anabolic hormones. It probably activates or increases the expression of some growth factors, okay? And it absolutely does. And so I'm going to show you guys a little bit of evidence on what we know happens with these anabolic hormones following resistance training. But I also want you guys to appreciate that there's a lot of emerging evidence that the hormone response to resistance training is probably not as important as what we once thought. Okay. As long as you make some testosterone or estrogen, as long as you make some growth hormone or some IGF-1, you have some kind of normal levels of those, then even though they go up after exercise, you're going to get a normal response. Where things get a little wonky is if you don't have, like if you have a lower than normal response, you're not going to get as much hypertrophy. Or if we really supplement on top of a normal amount, we give you extra testosterone especially, or a testosterone analog, or extra growth hormone, then we can really kind of push things up above and beyond what we would normally get. Okay, so we're going to see changes in turnover in myosin proteins very quickly, usually within several days of doing resistance training, but it also tends to take maybe 6 to 8 weeks for us to see noticeable, measurable changes in muscle size. Okay, so if we're in a situation where Katie wanted to go and have more defined muscles, she wants to have a little bit bigger muscles, she's got to go and work out consistently for maybe 6 to 8 weeks before she's going to be able to see any kind of actual improvements or changes in her muscles or her muscle mass. Now, she should hopefully see changes in strength within 1 or 2 workouts very, very quickly, but it takes a while to see noticeable increases in muscle size, which is one of the problems with resistance training and why people tend to have a hard time sticking with it. Is it's a slow process. I want bigger muscles now for whatever reason. I want them now, right? I don't want to wait 8 weeks. I don't want to have to go 3 times a week for 8 weeks before I see some kind of noticeable difference. So keep all of that in mind. Okay. So we've talked about this. I'm going to come back and talk about hyperplasia. Oh, is that all that I don't have any more about the anabolic hormones? Okay. So Before we talk about hyperplasia, I'll mention just a couple of things about the anabolic hormones. I'm not going to ask you test questions about this. I just want you guys to kind of be aware that this is a thing that happens. You go and you resistance train, and you're going to get an acute increase in testosterone that's going to start during the actual bout of resistance training, and it's going to go up and stay up for a little while afterwards. That increase in testosterone very often will drive a concurrent increase in growth hormone coming out of the anterior pituitary. Okay. The increase in testosterone and the increase in growth hormone drives an increase in something called insulin-like growth factor 1, which is made both in the muscles and in the liver. And so the combination of all three of those things are to bind to receptors either on the surface of muscle cells and other tissue cells, or to get into the muscle cells and bind on nuclear bound receptors, and to stimulate the genes, turn on the pathways that will lead to making more actin and more myosin. Okay, that's the general idea behind those. It is remarkably more complicated than all of that, but that should work for kind of what you guys would want to understand right now. And so when I just give myself testosterone, I activate those pathways, those same pathways, without having to do resistance training. And so, like, you can take testosterone and sit on your couch and, eat potato chips, and your muscles are going to get bigger than what a normal person can get simply by going and doing kind of perfect regular nutrition and perfect resistance training. And then you take testosterone and then you add a workout like resistance training on top of that, and that's how you end up looking like my dude here in our picture. Okay. All right. So I mentioned to you guys earlier this idea of what's called hyperplasia. And hyperplasia is a phenomenon that we tend to see in some animal models, especially in like rats and mice and cats, where if we have them do some kinds of resistance training, which it's some crazy stuff that we do in them to get them to resistance train, that they will take and like they would have 2 muscle fibers and they would split then into 4 muscle fibers. So 1 fiber becomes 2 fibers become 4, whereas what we think tends to happen in humans is I have 2 fibers and then both of those fibers are going to hypertrophy, but I still only have 2 fibers. Okay. Really, really hard for us to know for sure if this happens in humans or not, because to know for sure, I would have to take Kelly and cut out her bicep, have one of my graduate students count every muscle fiber in her bicep. Then we'd have to go back in and surgically replace her bicep, have her do resistance training for say 12 weeks, and then cut out her bicep again, and then have my grad student once again count all of the individual muscle fibers and compare our numbers. And so it's really difficult for us to kind of have good data. We use stuff from cadavers and they'll count muscle fibers from certain muscles in cadavers and kind of compare them across ages and training histories and things to try to get some idea of if they think that's what's happening. And it seems like that's probably not the case in people. Okay, so we're going to finish up today talking about some neural adaptations and then a little bit about what happens with bone and connective tissue. As I mentioned earlier, neural adaptations are the idea of a learning effect. You've gotten better at performing the motor pattern to perform a given task. Okay. So if you think as you've ever done something that you've never done before, you feel very uncoordinated, right? Like try to remember what it was like to learn how to ride a bike, or the first time, I don't know, if you were a dancer, the first time you did a particular dance step, or the first time you did a relatively complicated lift, if you were doing something like a squat or a power clean, that's going to involve kind of multiple muscles, things that you do initially when you feel very uncoordinated. As you practice that and you get better, that's a neural adaptation as the nervous system learns how to turn on the muscles in a more efficient manner to perform that task. Okay. So we can very often see neural adaptations as soon as after one bout of resistance training. So in a normal semester, when we do our resistance training lab, which would be the next thing that we would do, what would happen is we would ask everybody in class to check their 1 rep maximum strength on a bench press. It's my absolute favorite day in class. It pains me that we don't get to do it, because what happens is we have some people that have been very good at doing the bench press and have done it before, and we get a lot of people in class that have never done the bench press, and then hilarity ensues, where people are kind of getting really excited and trying to do good, and then people laugh, and it's a kind of, as they're at their inability to do a bench press, it's a really, really kind of fun bonding day in the lab. But what you guys are going to do is I'm going to have you guys come in and you're going to do a grip strength thing, which we normally do, but we can do the grip strength where you can kind of come in one at a time and we can stay distance and you can do it and I can wipe it off and then somebody else can do it again. So you guys will come in. Probably most of you don't do a lot of like grip strength testing in the way that we're going to do. And so next week we'll test your grip strength. Let's say that you could grip 50 pounds. If we came back in the next class period and had you do it again, then there's a very reasonable possibility that you're going to be stronger simply from having done the test and having practiced it. Okay. That's a neural adaptation. You did one bout of exercise with something, and you're going to almost immediately see the nervous system learning how to do things. Really, really cool stuff. We do some research on all of this in my lab. There's fun stuff that I can practice grip strength with my right hand, and then my left hand also magically gets stronger. As stuff crosses the hemispheres in the brain and all the motor neurons are in the same place in the spinal cord. Really, really cool things that can happen with these neural effects. Okay. But these are going to occur way before any change to the muscle itself. If it takes 6 to 8 weeks to see noticeable changes in muscle size, that means that all of the strength gains that are going to take place in the first, say, 6 to 8 weeks in a training program are most likely going to be exclusively the result of changes in nervous system turning on the muscle that you already have. And these nervous system adaptations are going to be very, very specific to the type of exercise that you're doing. Okay. So you do grip strength, you get better at doing grip strength. Doing grip strength is not going to magically make you better at doing squats. Okay. Doing squats in a squat rack is going to make you better at doing squats on a squat rack, but maybe not better at doing a leg press, even though they use relatively similar movements and relatively similar muscles. Okay. So the neural adaptations are very, very, very specific. When we get into next week and we talk about how we want to train, one of the things that we're going to spend a lot of time talking about and hammering home is this idea of something called specificity. And it's just that you're going to get better at doing whatever it is that you're doing. And so you need to train the muscles that you want to get stronger or that you want to get bigger, right? You need to train those muscles and isolate those muscles and not a different muscle, right? So if you want to get better at jumping, you need to train the muscles that one uses for jumping. Like doing a bench press is not going to help you. It's not specific enough to say being a better jumper or a better runner. But if you're an offensive lineman in football and you got to work on trying to push people away from you like this, then that would be an instance where you would want to do a bench press. Okay. So typically early in training programs, especially with people that have never done those kinds of lifts before, we see these very, very big neural increases in neural factors. Okay. So look at this panel here on the right. Training time, there's going to be this kind of steady, gradual increase in muscle size, right? Early on, you're going to get this big increase in neural factors. But then at some point, and this is another part about strength training that can be very frustrating for people, is that at some point, your nervous system has gotten about as good as it's ever going to be able to be at turning on the muscles in the correct pattern for performing the lift or that you're doing, right? And so once we've kind of blown through much of those early neural factors, then there's not much else that you can do. If you can recruit all of the motor units for that muscle, you're not going to magically add more motor units. There's nothing else for it to do. And so what we tend to see, especially in people that are very untrained, is they get a lot stronger really, really quickly. And then as those neural factors kind of get learned and they get kind of I don't know what the right word is. They're going to tend to plateau off. Like you've gotten better and better and better. And now like we're about as good as we can be with the amount of muscle that we have. The neural factors are going to stop going up. And so strength will then tend to, in some ways, plateau a little bit. And that frustrates people. They're like, oh, well, I was getting way stronger. Like I was lifting more weight. Like, every time I came into the gym when I first started because I was getting better and better. And now I've been doing this for 6 months and I've been lifting the same weight for a month and I'm really not getting noticeably any stronger. And that's because the neural factors have been maxed out. And all that's really left to be able to make your muscles stronger is to be able to increase their muscle size. And at some point, you max out the muscle size. And so, really, all that you've got is I have been lifting consistently for 2 years or 3 years or some period of time. My muscles are as big as they're probably ever going to get. My brain is as good as it's ever going to get at turning those things on. And so then my strength is mostly just going to plateau off. And I've now reached my genetic potential, right? I'm as big from a muscle standpoint and as strong from a muscle standpoint as I'm ever going to be. And what you will see then is in people that do like weightlifting competitions and stuff, these very, very advanced lifters, probably the only way they can get even a little bit stronger is to try to find some different neural adaptations. And so they'll do the same exercise with the same muscle groups, but they'll change it around ever so slightly in an effort to try to get a little bit. And they'll fight for that last couple of pounds that they're gonna have there. And that's just the nature of how all of these things are going to go. Okay. So we talk about bones and training. Bones change with resistance training by depositing more calcium onto the bones and making the bones bigger and stronger. Okay. So we call the deposition of the amount of calcium in those muscles as that's called bone mineral density. You want dense bones, right? You want your bones to be big and dense like my poor basset hounds because they're kind of squatty. They've got these really, really dense bones. Their bones are very heavy in comparison to, say, dogs that are meant to run fast and stuff. The bassets are built for kind of shock absorbing things. And so in people, we want the same thing. We'd like to have as much bone mineral density as we can. So the next time that we fall over, we don't break our hip or we don't break our leg or our wrist or our ankle or something like that. So the problem with bones is that changes in bones are going to be even slower and take longer to occur than changes in muscle size. And so it may take 6 to 12 months for there to be changes in bone mineral density. And so it's really hard for us to study these things because you got to train people for a long time. You've got to follow them for a very, very long time. And so, it's going to take a while. And so as we age with things, this is what's going to happen. Here is the look at what we call the femoral neck. Okay, so this is the neck of the femur where it's going to connect here in the hip at the acetabulum. And here's going to be kind of a young, healthy person, what the matrix on the inside of their bone is going to look like. Okay, here. And then here on the right is, let's say, an older person who has lost calcium out of those bones. Okay. Or you could say, here's an older person who has lost the calcium. Here's an older person that has done some resistance training and has held on to that calcium. And so because this one on the right is more porous, it's going to be weaker. And so when that person falls over and lands on their hip, they're at a much greater increased risk that that hip is going to fracture. And we'll talk about sort of once you fracture a hip, mortality rate goes up like 50% within the next like 2 years and things. There's a lot of really, really kind of bad things that are going to be associated with that. So the more you resistance train now, and the more you resistance train throughout your life, the more bone mineral density you're going to have, okay? And especially in women who post menopause are going to, as their estrogen declines, they're gonna lose a lot of their signal to deposit stuff, and they're going to increase degradation of calcium out of those bones. Resistance training can be a really, really, really important piece. Or if not resistance training, then things that are going to put high forces on your bones, running, sprinting, jumping, things like that, can be really, really beneficial from that standpoint. Okay. Similarly, in connective tissue, right? These are going to be what you can see with some of this is going to be collagen fibers and things that are going to be in your connective tissue. As we train, connective tissue is going to go up. Okay, ligaments and tendons and other connective tissues are going to get stronger because you're going to put down more collagen into those tissues. The ligaments is going to get bigger around. It's also going to become more elastic and stretchy. And so that's going to potentially help us limit and prevent injury as muscles increase in size and strength. One of the hallmarks in athletes that are taking steroids is they get a disproportionate increase in muscle size and muscle strength to their increase in the size and strength of their connective tissues. So the muscle grows faster and gets stronger faster than their connective tissue does. And so you see lots of connective tissue injuries in people that have taken steroids because their muscles are really big and strong. They can apply all these really high forces, and their connective tissue hasn't caught up to all of that yet. Those two things are out of balance, and therefore we see this kind of higher propensity for tears and strains and things that are going to involve the connective tissue. Okay. All right. And so we spend almost no time talking about disuse, although I could probably teach an entire class on what's happening from an atrophy standpoint. Some really interesting situations that are going to be these kind of adaptations to disuse. So space flight is a model of not so much disuse, but unloading, as is bed rest, as is having a leg or an arm or something in a cast. And the simple take home for when you don't use a muscle is it atrophies and it gets smaller. If you don't use it, you will in fact lose it in that way. And there's a host of other things. Basically, everything that changes in a positive way in response to resistance training goes in the exact opposite direction when we have disuse. Fiber size decreases, mitochondrial number and enzymes go down, fiber types go from being 2A back to 2X. You get much, much weaker. And there are these decreases in protein synthesis. And you would be amazed at how quickly we can lose muscle and muscle can go away. Okay. Stop sharing my screen. And I will very, very quickly share one very small sort of little anecdotal story about muscle atrophy. So one of the things, so my PhD advisor worked for NASA. I don't remember if I've told you guys that before. Before he came to the University of Georgia, he worked for NASA. And so one of the things that NASA cares a huge amount about, like if we want to get to Mars, we have to be able to, fly for however many, a year and a half, or however long it takes us to get there in a zero gravity environment. And so when there's no gravity, you can't resistance train, right? Because weights don't have any weight, like they don't weigh anything in space. Or when you try to walk, there's nothing to put, like there's no need to generate force because there's nothing to kind of push against. There's no gravity. It's this really weird situation. And so what they found in their early space flights was that you go into space and you're up there on the, like on some of those even short-term missions, and guys' muscles would shrink. They would get much, much smaller. And so because he had done a bunch of work with that, we were asked to do a study for a drug company that thought they had found a drug that would prevent atrophy, which would be a really, really, really great thing because we see muscle atrophy in response to chemotherapy and radiation treatments. It's called cancer cachexia. But you see it with aging and sarcopenia. You see it with space flight. You see it with people that are kind of doing bed rest stuff. They've been in the hospital for a long time. If we could give people a pill to prevent atrophy, it would be this just kind of wonderful, wonderful, wonderful thing. So they asked us to do a study to see how much atrophy we could get so we could develop a model to then try to give people this drug and see if it would prevent it. And so here is my question, okay? Tessa, are you there? We're going to ask Tessa a question.
Okay.
Okay. What would you let me do in an experiment if I paid you $1,000? Okay. Would you let me? You don't have to. I'll give you a scenario. You don't have to just like wildly come up with things. Okay.
Okay.
That's probably in everyone's best interest. Um, if I gave you a shoe that had like a 6-inch platform on it, okay, and I give you a right shoe and it has a 6-inch platform, and I give you a set of crutches, and I tell you that you have to wear that platform shoe all the time, and you have to go around all the time on the crutches. And so when you're on your crutches with that platform shoe, your left leg never makes contact with the ground. It's swinging freely. And then when you sit down in class, you have to prop your leg up. Okay. When you get up in the middle of the night and you want to go to the bathroom or you got to let your dog out, you got to hop on one leg. Okay. So that, basically we create a scenario whereby you do not bear any weight or any load on one leg for an entire month. Do you think you would let us do that for $1,000?
No.
Okay. So all of our people that did let us do it to them for $1,000 were all very regretful. They're like, we would never do this for $1,000 again. It needs to be like 2,000 or 2,500, or there is a number somewhere. But we did a study like this. The drug company gave us money. We paid them $1,000 to do all of this. They had to come by the lab every day, and we would measure the temperature of the skin on their legs to make sure they hadn't been moving. Your leg gets cold in the midst of that. And so in a month, their calves shrunk by about 16%, and their quads shrunk by about 12% in a month. Then about half of that occurred like in 2 weeks. So within like 2 weeks of doing all of this, right, their calf was almost 10% smaller. So I say all of this that when we unload muscles and we do some of these things like with bed rest and stuff that you're going to see in clinical populations, we lose muscle way, way, way faster than we're ever going to be able to gain it and add it back in. So keep all of that in mind. You guys are going to encounter in a lot of the jobs that you want, you're going to encounter people that have experienced very significant muscle atrophy, right? They've had an injury and they've come to you to rehabilitate them. They're going to have experienced a lot of atrophy. Or you're going to be, right, you're going to be a physician, or you're going to be a PA or something, and you're going to see people that are experiencing atrophy, or you're going to have to put them in the hospital for a while and they're going to get atrophy. Or you're going to want to train people and they're going to come to you and well, here's what has happened. So atrophy is a really, really big deal. And we understand a lot of it, that it's, a lot of it is just simply related to just contracting the muscles and some of those things. There's been lots of interventions to try to limit atrophy in that way. So, okay, well, that's good to know. For $1,000, Tessa will not participate in our lower limb suspension study. One of my grad students has a bright idea that we want to do not a long-term thing for a month, but we want to put people's arm in a sling for like 3 days and see like how much stuff changes in like 3 days. Tessa, would you let us put your arm in a sling for 3 days for like $100? Would you do that?
I'd do it for 200.
200. Okay. Tessa's a negotiator. If I said 200, would you have said 4?